Permutations. So, like I was saying, when you guys have permutations, place matters. And so, let's pretend all these guys are in a race, A, B, C, D, E, and F. How many different possible finishes are there? And so, what I'm saying is, how many different orders can they finish in? Okay? Now, this would take a very long time to list out. Like, a very long time. Because you would say, okay, let's say A, B, C, D, E, F. Right? That's one. Then you can say A, B, C, D, F, E. And then you could say A, B, C, F, D, E. And then I could just switch these two and say A, B, C. Oh no, we already have a D, F, E, huh? I can't switch those two. Okay, but I could switch these two. So A, B, C, E, D, F. Oh, these are all different, right? And we're not even close to listing all of them. This will take a long time. We need to come up with a better way of figuring this out. So, how many places are there if you have 6 runners? There'd be 6 places. And so, let's think about this analytically, critically, more efficiently. So, we have 6 places. How many outcomes are possible for the first finish? 6. How many outcomes are possible for the second place finish? 5. Right? There's one less because one already finished. And if you think about it like that, that kind of makes it easier. See, for this one, we have an A, B. Guys, you're too loud. You can talk to each other, that's cool, but not over me. So you have 6 options. But underneath the 5, we're only going to have 5 options. So let's say A finished first. How many options are there?
Oh my gosh.
B, C, D, E, F. That's a lot. Isn't it? And then after that, there's 4 options for third place. So that means for each of these, there's 4. So C, D, E, F. And then how many options are there for this one? 3. So let's say C finished. There's 3. So D, E, F. And then there's 2 options. So that would be E, F. And then finally, there's only one option, F. So this right here, A, B, C, D, E, F, is one outcome. This is getting gnarly, isn't it? So if I have 6 of these, I have to multiply all these outcomes by 6. And then right here, there's 5. And so I have to multiply all these outcomes by 5. And so on and so forth. This is called the counting principle. And what we're specifically doing with the counting principle is called a permutation. So what do you get when you multiply all these together? You get 720. There's 720 different outcomes for ordering this. And that is the same as 6 factorial. So this works just like how we did if we have as many places that we're considering as players. What if erasers? What if we had? What if we didn't care about all the other ones? What if we only cared about the first 3 finishers? The first 3 finishers. So what would that be? Like this right here would be the first 3 finishers, right? If we only cared about the first 3 finishers, it'd be 6 times 5 times 4. Hold on. It'd be 6 times 5 times 4. Can you guys think about that for a second? Let's see if we can adjust what we got right here. If we had 6, 1, 2, 3, 4, 5, 6, and we only chose 3 places out of those 6, how many different combinations would there be? It'd be 6 times 5 times 4. Right? Right? Because there would be 6 for the first one, 5 then 4. And how many total would that be? So it'd only be 120. Now, I can't say that this equals 6 factorial anymore. But can I change 6 factorial so that it does? Here's my question for you guys. What am I missing here? 3 times 2 times 1, which is? So I'm missing 3 factorial. Oh. I'm missing 3 factorial. Now, does that work for another scenario? Let's try this other scenario. So this one, we only chose three places. What if there was 1, 2, 3, 4, 5, and we only chose 3 places? How would that change? How many options do we have for the first one? No. These are 5 racers for the first 3 places, first, second, and third. So still first, second, and third. So it'd be 5 right here. And then 4. And then 3. Right? So is this equal to, okay, this is equal to 60, right? Is this equal to 5 factorial? What are we missing? Missing 2 factorial. 2 factorial? How do we know it's 2 factorial if we don't want to write all this stuff out? How many are we choosing again?
3.
Choosing 3. This is how you do it. Guys, watch it. Check it out. 5 factorials on top. On the bottom, 5 minus 3 factorial. Where did the 5 come from? Oh, there's 5 players. Where did the 3 come from? There's 3 places. That's how we're going to get our 2. This is how we do permutations. How is this subtraction related to up here? Well, up here it's kind of harder to see because 6 minus 3 is the same thing as 3 factorial. So where do we get this 6? There's 6 runners. Where do we get this 3? We're only choosing 3 places. So what if I didn't care about the third place for 6 runners? How would you find that one? It'd be 6 factorial divided by what? 6 minus 2 to give us 4 factorial, because that's what's missing, right? So we're missing 4 factorial, and so this would only equal 5 times 6, which would equal 30. All right, guys, here's the formula here I need to give you guys. Doesn't it? Here's your formula. N permutation R, so that's kind of like N choose R, is N factorial divided by N minus R factorial. This will tell you how many different outcomes you get if order matters. And I remember that order matters for this one because place matters when you're in a race. Order matters.